Okay, so we are done with one sample inference for proportion. So now we're going to look at the differences of proportions. So we're going to look at now two samples. I was going to wear one of my favorite ugly Christmas sweaters, this very grumpy cat. But then I realized I'm recording these videos during holiday break, and you all won't see these until late January, early February. So it'd just be ironic if I wear this sweater during then. I wouldn't put it past me, but I vetoed it. So at least you all can know that this is one of my faves. All right, so in more important news though, let's talk about the sampling distribution for the difference of proportions. So far we've worked with one sample proportions. Now suppose we want to compare the proportions of individuals with a certain characteristic in population 1 and population 2. We are going to call these parameters of interest P1 and P2. And the ideal strategy here is to take separate independent random samples from each population and compare the sample proportions with that characteristic that we're interested in. Now that's if we're doing surveying or sampling. Now, what if we want to compare the effectiveness of treatment 1 and treatment 2 in a completely randomized experiment or match pairs or block design? We're going to save those for means, but let's just suppose we have an experiment and we want to compare the proportions. Well, we are going to call these parameters still P1 and P2 in order to compare the true proportion of successful outcomes for each treatment. So we use the proportion of successes in the two treatment groups. So again, proportions, they don't like failures, they just like successes. But just because it's a success doesn't mean it's always a good thing. So here we have the following notation which we'll be using for this section of notes here. So I guess red. I don't know why I look outside the camera. I'm trained like on an episode of The Office, but it's just me in this house. So let's suppose we have population 1 or treatment 1 and population 2 or treatment 2. The parameter would be P1 for the true population proportion from group 1 or P2. The statistic would be P hat 1 versus P hat 2. And our sample size will be sample size 1 and sample size 2. So nothing too complicated with the notation here, still very straightforward. So we are now having two independent populations. Perhaps we're looking at like the United States versus Europe, or we're looking at California versus New York, or maybe we're looking at brown-eyed people versus blue-eyed people, etc. But we have our populations of interest defined, and we're trying to compare this proportion of successes within each of the two populations. Now, we still are going to have the same assumptions, thankfully. So it still has to be stated random, whether it's an SRS or random assignment. It still must be independent, and this time we must include both. So 10% condition if sampling without replacement, so that the degree of dependence is negligible. And we must state that P1 does not have any influence on P2 since they are independent. And this time we're also going to check the normality condition by large counts for both samples. So this is just kind of a wrap up here. We choose an SRS of size N1 from POP1, and same thing for N2. The shape, if both of these are at least 10 or more, then we can say the sampling distribution of P1 minus P2. These samples are approximately normal. Back to our study with independent random variables, we know that when we are looking at the difference of the means, we just subtract their centers. And same thing here, that in order to combine to find the standard deviation, you add their variances, and then you take the square root. So this is just more the formal definitions which we'll be working with. And then therefore, if all three conditions are met, then we should have the following picture. We should be approximately normal with the center of P1 minus P2 and a spread here of the standard deviation of P1 and P2. So suppose that there are two large high schools, each with more than 2,000 students. In a certain town at school 1, 70% of students did their homework last night. Only 50% of the students at school 2 did their homework last night, and the counselor at school 1 takes an SRS of 100 students and records the proportion that did homework, whereas school 2's counselor takes an SRS of 200 students and records the proportion that did their homework. School 1 counselor and School 2's counselor meet to discuss the results of their homework surveys, and after meeting, they both report to their principals that P1 minus P2 is 10% or 0.1. So let's go ahead and describe the sampling distribution here for the difference of the population proportions. So the first thing, right, shape, center, and spread. Let's go ahead and check our shape here. So in order to check the shape, we are going to need to verify a few things. So let's see. I'm going to thin this out a little bit. We believe, right, we have the parameter here. So we believe the proportion of students who did their school from P1 would be 70%. And then the sample size from the first group was 100 students. And then from P2, we assume it's about 50%, and the sample size there was 200 students. So next thing we need to check here is the normal condition, which that's going to be the shape. So we need to check N1 and P1, as well as N1 and the complement of P1. So again, substitution. So we show what we want to communicate, then we take our response here. So I'm going to have the following to check our success failure. And guess what? Lo and behold, 70 and 30 are both greater than or equal to 10. Okay, so now let's check for our second group here, our second population. Let's suppose we have 50% of the 200 students that we believe did their homework, which means another 50% did not do their homework. Well, guess what? 100 is most definitely greater than or equal to 10%. So we can say here that the shape is approximately normal by large counts. So that's good. We at least know the shape. Now, the next thing is that we want an unbiased center, and we were told some key information that they took separate SRSs. So that means here that the center of our distribution is going to look as follows. So now we're doing the center. We know that the mean of P1 minus P hat 2 is actually just going to be the difference of the parameters here, of the means of the original distributions. So the mu of P1 is just P1, and the mu of P2 is P2. So we're going to take the difference between 0.7 and 0.5. And so we actually believe that the differences of the population proportions is 20%. So that's going to be our center. And then lastly here, we need the shape. And since both high schools had 2,000 and 100 and 200 are both less than 10% of their respective populations, we have independence, which means we can construct the proper standard deviation here. So that's going to be the spread. So the sigma of P hat 1 minus P hat 2, remember, even though it's a difference, we still need to combine them. So we're going to take P1, remember we're adding their variances. But this actually, we have a formula for this, and that looks like the following. So I'm actually going to erase this part here. We have a formula for the difference of proportions here, and it's also on the AP Stats formula sheet. But we're going to take P1 and its complement, and we're going to divide that by N1. And even though it's the difference, since we're combining the spreads, right, two separate distributions with different spreads, you're always going to have more spread because you're just putting more variation between the data points and the means. So we're actually going to combine these two independent random samples using the following formula. So here, P1 was going to be 0.7, 0.3 out of 100, plus 0.5 times another 0.5 out of 200. And when I do this, type this into my handy dandy calculator, I get a spread for the sampling distribution of the difference of proportions to be about 0.0579. So our last thing here is going to be to wrap this up in a pretty bow. And why can't I find, oh, there we are. Okay, so the sample distribution between P hat 1 and P hat 2 is going to be approximately normal with a center of 0.2 and a spread of 0.0579. So that's going to be our sampling distribution for this sample in particular. And again, if we took every single possible sample, we should expect it to have these characteristics. Currently, we're just approximating because as we take more samples, we approach the truth closer to the truth. Okay, so now that we have our distributions, let's suppose, find the probability of getting a difference in sample proportions of P1 hat minus P2 hat. Well, this is easy now because we already have the sampling distribution, right? We just said that the sampling distribution between these two was approximately normal with a center of 0.2 and a spread of 0.0579. So next we're going to just draw this picture here. We believe we're at the center here at 0.2. And then 1, 2, 3, 1, 2, 3, 1, 2, 3, 0. And then here I'm just adding in the standardized z-scores here. If I were to go one standard deviation below, that would be at 0.14 something and so forth. So actually an observation of 0.10 is going to be somewhere right here in between the -2 and the -1 standardized z-scores. And I want that the difference is 10% or less. So I'm actually going to shade here to the left. So let's check. We've done our parameters. We've drawn a picture of the situation. Now let's do a probability statement. We want the probability that our sample difference, right, between the proportions is less than 0.10. Well, this is the same thing here. This 0.10 has a standardized z-score. So we are looking for the probability that this z-score is less than or equal to some value here. So let's find the z-score for 0.10 minus 0.20 all over 0.0579. We want the probability that an observation has a z-score less than or equal to -1.73. And I would either go to my table or my calculator, and we would find that the probability of obtaining a difference in sample proportions of 0.10 or less is actually going to be 0.0418. It's a very small chance that you're going to get a sampling difference of proportions 10% or less. So that's just an example there of how we construct the sampling distribution, how we look at the different parameters, how each of the conditions gives us more information about the shape, center, and spread of the sampling distribution, and then how we can use the sampling distribution to compute probabilities. What's going to happen in the next few lessons is now we're going to apply this difference of proportions to a new type of confidence interval and a new type of significance test. I tried not to hiccup on that one, y'all. Sorry.